Hi dear students, we are going to discuss determination of hardness of water sample by EDTA method. Means what? Here simply we are going to find hardness of water sample, that is how much hardness is there in the water, and for that which method we are going to use? EDTA method. So why EDTA method name is given? Because we are going to use EDTA chemical for finding a hardness. Okay. So here simple titration we are going to do here, that is the titration between water sample and disodium salt of EDTA. So two chemicals. For water sample I am saying it is a chemical, and that water sample you have to titrate with salt of EDTA. Try to understand, salt of EDTA, and that is a disodium salt of EDTA. So one structure in front of you, right, that is the structure of EDTA, and long form of EDTA is ethylene diamine tetraacetic acid. Okay, and this EDTA is partially, or you can say incompletely soluble in water, and because of incompletely soluble nature of EDTA, instead of EDTA we use salt of EDTA. So as far as this structure is concerned, this structure is of only EDTA, that is a ethylene. You just see at the center CH2, single bond CH2, that is the ethylene. Now that CH2 connected to nitrogen, left and right, two nitrogen, so it is a diamine. So two nitrogen group, that's why diamine, and each nitrogen connected to two acetic acids. So left hand side two acids, right hand side two acids. So how many acids? Four acids group, that's why tetraacetic acid. Now we will see the structure of salt of EDTA. Now see the difference. So if you see this structure, you can see out of four acids, two acids in the form of a salt, that is what? Sodium salt. So you can see left hand side, out of two acids, one acid is a salt, that is what? Sodium salt. And you can see the right hand side, out of two acids, one acid with sodium. So that is what? Disodium salt of what? EDTA. And speciality, it is a completely soluble in water. So if we take EDTA in the form of salt, then it is a completely soluble. Okay. And second most important thing, it is a highly sensitive. Sensitive towards hardness causing a metal cations. Sensitive towards hardness causing a metal cations. Even in very low concentration. Even in very low concentration. So that's why it is called as a highly sensitive chemical toward metal ions. Who is sensitive? EDTA is sensitive. Okay, and it reacts very quickly with metal ions. So these are the two main reasons behind use of EDTA for finding hardness of water sample. What are the two reasons? First, disodium salt of EDTA completely soluble, and second thing, it is a highly sensitive toward hardness causing chemical even in very low concentration. This is a very important. That's why disodium salt of EDTA is used for determining hardness of water sample. And if you see the structure of disodium salt of EDTA, you can see that four acids groups are there. So that is a four reactive centers, and two amines groups are there. So 4 plus 2, how many reactive positions are there? 6 reactive positions are there. That's why it is a hexadentate. and because of more reactive positions, because of more number of reactive sites, it is a highly sensitive, it is a highly reactive. So highly sensitivity or higher reactivity because of presence of more number of reactive positions, or you can say sites. Okay, and that's why it is used for determining hardness of water sample. Now we will see the reaction, how water sample react with salt of EDTA. So you see here, water sample containing metal cations. In the reaction you see water sample having a metal cations, for example M2 plus. We don't know which cation is there. It may be a calcium 2 plus, it may be a magnesium 2 plus, it may be a iron 2 plus. So here commonly I written M2 plus. It is in the water sample, and in that what we are adding? Disodium EDTA, right? But before addition of disodium EDTA in water sample, first you have to add buffer solution in the water sample, because buffer role is to resist change in pH. Okay, so first in water sample you have to add buffer. Why to add buffer? Because we have to maintain pH of water sample. And second thing you have to add, that is the EBT indicator, because role of indicator is to get indication about completion of reaction, because indicator will give idea about the completion of reaction through color change. Okay, so before addition of disodium EDTA in water sample, first we have to add buffer solution and EBT indicator in the water sample. Okay, and then we have to add disodium EDTA. Now what is the long form of EBT indicator? So it is a Erichrome black tea indicator. Okay, so once you add disodium salt of EDTA in the sample, you will get a complex. And what is that complex? Metal EDTA complex. And that complex is known as a cyclic coordination complex. So complex formation, right? How we get idea that complex formation take place? Through color change, right? And for that color change we are using EBT indicator. So here first we will see the principle. What is the principle of determination of hardness of water sample? So principle is very simple. Who responsible to make water hard? Metal cations like Ca2 plus Mg2 plus. So hardness causing ions like Ca2 plus and Mg2 plus present in water sample, and these ions responsible to make water hard, responsible for giving hardness to the water sample. So these ions form stable complex with whom? These ions form stable complex with disodium EDTA. Just now in the reaction, in the last slide, I shown that disodium EDTA forming a complex with M2 plus, and that M2 plus may be Ca2 plus or Mg2 plus. But for stable complex formation, we have to maintain suitable pH by using a indicator. So before adding a EDTA, we have to add buffer solution and EDTA indicator. And indicator we are using to get a sharp end point. Okay, so principle, hardness causing a salts, that is what the Ca2 plus Mg2 plus ions present in water sample, and that ions form a stable complex with disodium EDTA. But for getting a stable complex, we have to maintain suitable pH, and for maintaining suitable pH, we have to use buffer solution. And for indication of completion of reaction, or you can say that complex formation take place or not, for that we have to use EBT indicator. Now, we will see the clear-cut reactions. As I said, before adding EDTA, we have to add buffer solution in the water sample. So please see the first reaction. Water sample containing M2 plus. So in that water sample, you have to add buffer solution, and buffer solution pH is 10. So buffer 10 we are going to use, and in that we are adding EBT indicator. So 3 chemicals we are mixing. Please try to understand. Water sample, buffer solution, and EBT indicator. After adding these 3 chemicals, you will get first complex, and that complex is metal EBT complex. And what getting released? H plus ions getting released. And as you know very well that during a reaction, if H plus ions getting produced, then pH value of solution changes. But here we are using a buffer solution, and buffer solution will not allow to change the pH of solution. Okay, so in first reaction we get a first complex, and that complex is MEBT, and its color is wine red or pink red. Okay, wine red or pink red. Now here in conical, what is the color of solution? Wine red or pink red. That pink red or wine red color solution you have to titrate with EDTA. So how to titrate? In conical you have a wine red solution, and in burette you have to fill EDTA solution, and drop by drop you have to add EDTA solution in the wine red colored conical solution. So what will happen? This is the replacement of complex. Which complex? Metal EBT changes to metal EDTA. So metal EBT, wine red, and product is metal EDTA. So metal EDTA is colorless. And what getting released after reaction? EBT getting released. And what is the color of EBT indicator? Color of EBT indicator is blue. So what is the end point of titration? Wine red color solution you are titrating with EDTA, and you are getting a blue color solution. So blue color, who responsible for blue color? EBT getting regenerated again. Means EBT position or place taken by EDTA, and what getting released? EBT getting released. So simply end point of our titration is wine red or pink red to blue color. Once you get blue color, stop the addition of EDTA. And once you stop the addition of EDTA, you have to note the burette reading. And from that reading, we have to find out hardness of water sample. Alright. So experimentation part we will see. So experiment in 2 parts. First part, standardization of Na to EDTA. So in standardization part, first we have to find molarity of EDTA that we are using for finding hardness of water sample. So as far as theory is concerned, you need to remember part 1, standardization of Na to EDTA. So how to standardize disodium salt of EDTA? So for that purpose, we have to take a standard chemical, magnesium sulfate. You can take 25 ml, 10 ml, 20 ml. In that you add, according to that, you have to add buffer solution and EBT indicator. Okay. So here, as I said already, that the sample is magnesium sulfate. In that you are adding buffer solution. In that you are adding EBT indicator. You will get wine red color solution, and that wine red color solution you have to titrate with Na to EDTA. So if we summarize it, then what is there in the burette? Na to EDTA is there in the burette. What is there in the conical? Magnesium sulfate is there in the conical, right? And in that we are adding a buffer solution and EBT indicator. So end point of titration is wine red to blue color, right? Wine red to blue color. And once you get a blue color, you have to note burette reading as a Phe2 ml. We have to note burette reading as a Phe2 ml. Now we will see part 2. And in part 2, you have to find hardness of water sample. So here, the procedure that we seen in part 1, same procedure you have to follow in part 2, except only one change. And what is that change? Instead of using magnesium sulfate standard chemical, here you have to use water sample. So take 25 ml water sample or 10 ml or 20 ml as per your choice in the conical. Then in that you add buffer solution. In that you add EBT indicator. So three chemicals you are mixing together. Try to understand. In conical you are taking water sample. In that you are adding a buffer solution. Then in that you are adding a EBT indicator. So three chemicals you are mixing together in the conical, and color of that conical solution is wine red. And that wine red solution you are titrating with Na2 EDTA, that is the disodium salt of EDTA. So if we summarize it, then what we are taking in the burette, disodium salt of EDTA. What we are taking in the conical, water sample. What we are adding in that, buffer solution and EBT indicator. What is the end point of titration? Wine red to blue. And once you get a blue color, stop the addition of EDTA and note the second part reading YML. So in this way, you have to complete part 1 and part 2. Now what is the calculation? So first part we seen, that is the standardization of disodium EDTA, and for part 1 calculation we have a formula M1 Phi1 which is equal to M2 Phi2, and hope you remember that in part 1 we got burette reading Phi2 ml, and Phi2 ml is the amount of EDTA that you added from burette into conical for getting a blue color solution. So the quantity of chemical that we are adding from burette into conical, and we added, right, up to what time we added? Till wine red color changes to blue. So that quantity of EDTA is Phi2 ml. Okay, and M2 is molarity of EDTA. So magnesium sulfate M1 Phi1, EDTA M2 Phi2. So we know the molarity and volume of magnesium sulfate that we used. M1 Phi1 we know now, because molarity of magnesium sulfate is known. Volume of magnesium sulfate that we are taking for titration, that is also known. Divided by Phi2, and Phi2 is burette reading. So if you do that calculation, you will get value of molarity, that is the M2. Now what is the use of that molarity? That molarity is required to find hardness of water sample. If you see the formula of hardness of water sample, you can see that A is hardness of water sample, which is equal to Y into M2. So this M2 is what? This M2 that we got in part 1. So that M2 we required. So Y is what? We already seen in the experimental part of part 2. Y is burette reading. And what kind of burette reading? The time when we got blue color, right? We stopped titration and we noted burette reading as a YML. So that burette reading value YML multiply by M2, that is what the molarity that we calculated in part 1, multiply by 100. 100 is the molecular weight of calcium carbonate, multiply by 1000, that is what the volume of solution in liter, 1 liter 1000 ml, divide by Phi. Phi is what? The volume of water sample that we are taking for titration. As I said that you can take 10 ml, 20 ml, 25 ml, 50 ml, 100 ml, whatever it may be. That given value will be the value of Phi, and Phi is a value of volume of water sample. So this is what the complete information about the determining or determination of hardness of water sample by EDTA method. So dear students, here we seen the principle of EDTA method, we seen theory behind it, we seen the complex formation reaction, we seen the separate reaction with EDTA as well as EBT. Then we seen the experimentation part 1, part 2. Then we seen calculation of part 1 and calculation of part 2, and in part 1 we got molarity of EDTA, and in part 2 we got the value of hardness. So dear students, here you keep in mind, if untreated sample is given without boiling, you will get total hardness, and if you take a boiled water sample, you will get permanent hardness. Keep in mind, for total hardness and for permanent hardness, same formula you are going to use, same formula. Okay, So only one thing you keep in mind, boiled sample will give you permanent hardness and untreated, unboiled water sample will give you total hardness. Okay. And once you get total hardness and permanent hardness value, you just subtract permanent hardness value from total hardness, you will get temporary hardness value. Okay. So in next lecture, we will see numericals on hardness of water sample. Hope you understood. Thank you. Thank you for watching.